So we're gonna dig in this idea of the Jacobian. So the whole premise is this, just to kind of set the stage. It's about this. When we go from rectangular to polar, that dA, I hope you kind of have that visual now of that dA multiplied by z, get the volume of the prism, all that stuff. That dA in rectangular, dx dy, is a different geometric design when we go polar. So it requires different formulation. So the dA goes from dx dy to r dr d theta. And then you've now seen, maybe not without full justification yet, but you've now seen with spherical coordinates how a dx dy dz rectangular little prism dv becomes rho squared sine phi d rho d theta d phi. Like, how does all that happen? So the background that you now have seen, this idea of Jacobian, after Carl Gustav Jacob Jacobi, the Jacobian. So he's the one. So if you want to go to math history, just Google math history and Jacobi, and you can read about his history if you like. But it's the whole connection and the math behind it. It's just fascinating to get into the human side of it. So if you're interested, feel free. But I'm just gonna, on a more practical sense, take you through a maybe not highly rigorous mathematical proof, but a more unfold the story so that you can kind of see the progression of where this stuff comes from this Jacobian idea. And I'm going to take you back to Calc 2 in order to do that. In Calc 2, you may have seen an integral that looked like this. Let's say x times e to the x squared dx. And to do this, this problem, you may have used a U-substitution. You may have said, hey, let's let u equal x squared. And when you let u equal x squared, then the derivative of u with respect to x, du dx, would have been 2x, which means if we multiply the dx differential over du is equal to 2x dx. And so all of this was just kind of our design to take an integral that was kind of messy and turn it into an integral that was not so messy. Look, if you let u equal x squared, then it becomes e to the u. And let me just change my color a little bit here. If we notice that du is 2x dx, so what we could do is just put a 2 there. 2x dx. You can't just put a 2 there. Not without putting a 1/2 here. Do you see? 1/2 times 2. Okay, so 2x dx is the same as du. And so we can replace 2x dx with the du, and don't forget the 1/2 out front. So we've converted an integral from being a messy integral in terms of x to being a very simple, integral of e to the u du. Not so hard to do. It's just e to the u plus c. So it turned into something easy. So kind of likewise, you've seen it now, I hope, that when we go rectangular to polar, it's an option. It's a strategy so that we can maybe make things a little bit easier. And in doing so, when we had a Calc 3 double integral over some region, and we had a function in rectangular coordinates, and we had our dA, suppose we wanted to make that conversion to polar. So the first thing is, from our polar coordinate conversions, we know that x becomes r cosine theta, and we know y becomes r sine theta. So instead of f of xy, we would have had f of r cosine theta, r sine theta. And our dA in polar coordinates would have been r dr d theta. All right, but let's talk about where does that come from. So up here, we can't just erase dx and make it du. We had to figure out. So in this case, as we were converting to a different coordinate system, really, from x being in terms of x to being in terms of u, we started with this conversion, u equals x squared, and we found the one and only derivative du dx that there would be defined. Now, in this multivariable world, we don't get to choose as we move to polar coordinates. We have to go with what is mathematically known, that x is equal to r cosine theta and y is equal to r sine theta. So you have here, we would let u equal x squared and then find du dx. down here, we don't get to just randomly pick or choose based on the function. We just have to take the actual conversions from rectangular to polar and say x equals r cosine theta, y equals r sine theta. And then like up here, we would do a du dx in order to figure out how to convert dx into a du. It's not just erase it and make it du. It's, du is 2x dx. Kind of like r dr d theta, 2x dx. That's the relationship. So likewise down here, we have to take some derivatives. But it's a multivariable function. X is a function of r and theta. So we're going to need a partial derivative with respect to r. We're going to need a partial derivative with respect to theta. We're going to need a partial derivative with respect to r and a partial derivative with respect to theta. And we organize those 4 partial derivatives into a 2x2 matrix, or what's known as a determinant Jacobi, called the Jacobian. All right, so up here it was just the one and only one derivative there could be. Now we have 4 partial derivatives. And up here where you just now work by, multiply by dx, look at that relationship and figure things out. Now we've got a 2x2 determinant. Now, if you think back to our cross product days, remember back in our vector units and cross products, we can evaluate a 2x2 determinant by saying this product minus this product. That's how you evaluate a 2x2 determinant. Thank you, Jacobi. So let's do it. All right, so I'm going to come down here so I have some room. dx dr. The derivative of x with respect to r. So the cosine of theta is a constant. So the derivative of a constant times r with respect to r is just the constant. Should we just go down? dy dr, same kind of a thing. dy dr, the derivative of y with respect to r, the sine of theta is a constant. So the derivative would just be sine theta. Dx d theta. All right, now r is held constant, so it's going to come along for the ride. And we're going to take the derivative of cosine, which is negative sine. And then r sine with respect to theta would be r. The derivative of sine is cosine. So we end up with this 2x2 determinant. So we'll do that cross product and subtract. So cosine theta times r cosine theta minus sine theta times negative r sine theta. So do you see the double negative there? It's going to be negative r sine theta times sine theta. I guess I went that way, but the product is the same either way. So it all comes out to be this. Look, we've got r cosine squared theta. We've got plus r sine squared theta. We've got r times the quantity, if we factor out the r, cosine squared theta plus sine squared theta. And I hope you recognize this Pythagorean identity. Cosine squared plus sine squared is equal to 1. And so this comes out to be just r times 1, which is equal to r. There it is. So just like over here, we had to see that relationship that du is 2x dx, or ultimately 1/2 du was x dx. So to make the conversion, we had to replace x dx with 1/2 du. Kind of the same way here, we have to replace our dx dy with r dr d theta. So this is the process that we run through to kind of see where these things are coming from. Now there's also the geometric proof. Back in that module with polar coordinates, you saw more of a geometric definition or explanation for where the r dr d theta comes from. But here's a Jacobian explanation. Now, as we moved into triple integrals, if we had a triple integral over some region E, and we had a 3-variable function, and we had a dv, and suppose it made sense, like you've seen now, suppose it would make sense to convert that into a cylindrical coordinate situation. Remember, cylindrical coordinates were polar coordinates extended, so cylinders. And so we would make the conversion. X would become r cosine theta. y would become r sine theta. And this is the tough one. This is the really challenging one. Z is equal to z. But then dv became r, dr, d theta, dz. This was all dv. So again, we can make a geometric argument much more challenging in a cylindrical realm, or it maybe makes a kind of intuitive explanation because it is just cylindrical coordinates extended. So why wouldn't it be r dr d theta again? But we can also make a Jacobian argument for this. So notice up here, we had the one relationship between u and x. We had the one derivative. Then here we had the two relationships between x, r, and theta, y, r, and theta, which means we had four partial derivatives. Now, this is still true. This is still true, and now we have this. Now we have three relationships. Yes, the one is z equals z, but nonetheless, three relationships. So that means we would have a Jacobian that would have this. We'd have a partial with respect to r for each of the three relationships. We would have a partial with respect to theta for each of the three relationships. And we'd have a partial with respect to z, because notice x, y, z becomes in terms of r, theta, and z in cylindrical coordinates. So r, theta, and z. And so we end up with a 3×3 determinant that we can evaluate. And the idea would be this 3×3 determinant should spit out that Jacobian of, my mug is in the way, that Jacobian of r, just like it spit out the Jacobian of r here, r dr d theta. Now it should spit out a Jacobian of r once again, so we have r dr d theta dz. All right, let's do it quick and see. Now I say quick because we've already done much work with this, like dx dr we've already done, dx d theta, dy dr, dy d theta. We've already done those, so I'm going to just do them really quick here again. dx dr, dy dr, dz dr. Take the derivative of z, which is equal to z, with respect to r. dx d theta, dy d theta, dz d theta. Now watch this. dx dz, the derivative with respect to z. So if you're taking the derivative with respect to z, we hold r constant, we hold theta constant. This is just a constant. And the derivative of a constant is 0. Same thing. The derivative of z with respect to z, though, would be 1. Now, see if this rings a bell. Go back to cross products with vectors. Remember we had I, J, K, and we would do that thing where we would grab the I, take out the row in the column, be left with the 2×2 determinant. Same routine, except instead of I, J, K, we've got cosine theta. By the way, thank you, Jacobi. We can take cosine theta times its minor determinant. And its minor determinant is going to be this cross product. R cosine theta times 1 minus 0. And then we grab this next one. It would be a minus r sine theta times its minor determinant. So if we take out the column and the row, we're left with sine theta times 1 minus 0. And then see if this rings a bell. I don't know what I just did, but I just made my mug really big. What? Get out of the way. I just like to be able to have you see me. Remember, when we did this, it was whatever happened here plus, whatever happened here minus, whatever happened here plus. Remember the plus minus plus deal? So plus minus plus. And the plus, now watch this. When we get to this one, it's going to be 0 times its minor, which would be 0 minus 0. So not so interesting. Do you see it now? Factor out the r, cosine, cosine, minus, minus. Factor out the r, sine, sine. Ta-da! R d theta dz. The Jacobian. All right. Now, let me just change colors for this because I'm actually going to let you do some work. And the work I would like you to do is this. When we went spherical, we had a triple integral over some boundary, some region. We may have had a function in rectangular coordinates and we had a dv. And we converted that. We first had to replace x with its connection. If you go back, I asked you to try to figure these out using some trigonometry, but of course they're in the handout that you could download. They're in the video by Bazette. But there was a relationship here. I want you to go look it up. There was a relationship here. There was a relationship here. And the way this one worked out, but I want you now to figure it out from a Jacobian perspective, the dv became rho squared sine phi d rho d theta d phi. Huh. So where did that rho squared sine phi Jacobian come from? Well, it came from a 3×3 determinant, came from a whole bunch of partial derivatives. So you need to find what x was, what y was, what z was. You got to take all 9 partial derivatives. You got to evaluate the determinant. I want you to try. So when you advance to the next slide, you'll see it. Hey, go try this, figure it out. And then I'll have a video to confirm your work. All right. I know this one's getting long, so I'm just going to stop here. But I think, no, I can't stop here. Because you can do this on Wolfram Alpha. Oh, no. You can do this on Wolfram Alpha. So just regular Wolfram Alpha, no widgets this time, just regular old wolframalpha.com. If you type in determinant of, because that's what you're doing. You're trying to devaluate a determinant. In the case of the cylindrical coordinates, it was that 3×3 determinant. And here's the notation. First, you need a set of braces around the entire determinant. Like on paper, we would have gone the boom, boom. On Wolfram Alpha, you need brace, brace. And then inside the braces, you put braces around the rows, not the RHOs, the ROWs. So the first row, if you look back, was cosine theta, negative r sine theta, 0. So put that in braces. The second row was sine theta, r cosine theta, 0. And then the last row was the 0, 0, 1. Was the 0, 0, 1. And so when you enter on that, Wolfram Alpha will interpret that as a determinant, but boom, it'll evaluate that determinant, but boom, and it'll show you the R. So I'm showing you that because I would like you, for the experience, to slug through the 3×3 determinant for the spherical coordinate system to discover the Jacobian of rho squared sine phi, just because it's a good experience. If we were in the classroom, you'd have done it. So I'm just going to ask you to give it a shot. But just so you know, you can also ask Wolfram Alpha to slug it out for you just for fun. All right? So advance to the next slide. You'll see the instructions about that.